Hey, welcome back to Fun Maths. Today we're looking at instantaneous rate of change. Perfect. Now, we have looked at the average rate of change in the past. However, in this particular section we are looking at instantaneous rate of change. Now, to get your head around this, we need to consider tangents or the tangent line at a particular point on a graph. So again, let's consider the following. Here you can see the equation. It's the red one here. That's y equals x squared. It's not a straight line. It's not linear. In this particular case, if you consider this particular point here at the coordinate 1, 1, what they've done is they've drawn some secants of varying lengths. And you can see the first one here, they've put another point here at 2, 4, and they've drawn from that original point to this one here, they've drawn a secant. And you can see the slope or the gradient of that particular line. Now, the whole idea of this instantaneous rate of change is that if you make the secants smaller and smaller, so closer and closer to the original point, you can see that the gradient or the slope becomes more like the tangent at exactly that point, or at that instantaneous point. And so this particular exercise, what we're going to be doing is we're going to be finding a point, and then we're going to be finding another point that's just a little bit away from the original point, and we're going to create a secant, and we're going to find the gradient of that little line between them. And the closer or the smaller we make that, we're saying the more accurate we're going to get a representation of that instantaneous rate of change at that particular point, because it'll become just like the tangent at that particular point. So let's have a look at this here. It says, estimate the instantaneous rate of change of y with respect to x at the point 2, 9 on the curve y equals x cubed plus 1. And they're saying, hey, what we're going to do this is we're going to consider creating a secant between some points, both P and another point Q. But what we're going to do is we're going to choose a point here that's very, very close to 2. And they've decided, hey, we're going to choose 2.01. So you can see it's pretty close, and when you substitute in 2.01 into this equation here, y equals x cubed plus 1, obviously its y coordinate is going to be 2.01 to the power of 3 plus 1. Yep. So again, once you've got these 2 points and they're pretty close together, we know how to calculate the gradient between 2 coordinates. So it's going to be obviously the y2 value, take away the y1 value, so this here, let me get my texter out. Yes, it's going to be this one here, take away this one here, divided by this one here, take away this one here. And what you can see here, we get the gradient is 12.0601 between those particular points. Now, what you could do even, which is even pretty cooler, is if you found another point that was even closer to 2, and they're suggesting, okay, rather than 2.01, how about we did 2.001? Wow, that's pretty close to 2. So we found another point. If you did the same thing, you substituted that into the equation here, you got its y coordinate, and then you found out the gradient on that, you would find it's going to be even closer to 12 in this particular case. Yep. You could keep on going further and further, go 2.0001. Whoa. And then it would be an even more accurate answer there. Cool. Next one, we've got worked example 11. It says here, the graph represents the area covered by a spreading plant. Area is measured in square centimeters and time in weeks. Cool. First one is saying find the gradient of the secant between point P and point Q. So imagine that there's a line joining those together, which is the secant. we know how to calculate the gradient of those. It's going to be the y2 coordinate, take away y1, divided by x2 take away x1. We can run that calculation, and in this particular case we get that the average, the gradient is 60. Okay, now like we were talking about before, if we make the secant even closer, then we're going to get a more accurate representation of the instantaneous rate of change. So this now saying, hey, consider this particular point here, which is Q dashed, and it's happening at 3,330. It says, hey, find the average rate of change of area with respect to the time for the interval between 2 and 3. Yep, so we're going to do that between those 2 points. And then it says, hey, and hence estimate the instantaneous rate of change of the area of the plant at time equals 2 at this particular point. At this particular point, from 2 to 7, we saw that the average rate of change was 60 centimeters squared per week. And now they're saying, hey, what's it going to be between these two here? So again, you would find out the gradient between these. So it's a 330 take away 300 on the top line, divided by 3 take away 2, which is 1. And we get that the gradient at this particular point is 30. Now, given that the secant here is a lot shorter than this one, this is more like the instantaneous rate of change because it's a shorter secant. And so what we can say is we can estimate the instantaneous rate of change at this particular point based on this shorter secant. We can say that it's approximately the 30 centimeters squared per week. If you did an even smaller secant and you had some values, you'd get an even more accurate instantaneous rate of change. Alrighty, this one here, it says consider the curve. We've got y equals 2 to the power of x. That's cool. It says using the secant through the points where x equals 3 and also when x equals 3.1, it's saying estimate the instantaneous rate of change of y with respect to x at the point where x equals 3. So what we're going to do is we're going to substitute 3 into this equation and find out the coordinates of what's going on. So when we do that, when x equals 3, y is equal to 8, because 2 to the power of 3 is 8. We're going to do the same thing when x equals 3.1, substituting it into the equation, you get y equals 8.5742. Perfect. We can then calculate the gradient between those 2 points. So in this particular case, we're going to do obviously this value, take away this value, divided by this value, take away this value. We get that the gradient is 5.7419. Cool. So you can say at x equals 3, because we've found a point, created a secant that's pretty close, our estimate is at the instantaneous rate of change at x equals 3 is that there, 5.742. Now, if you wanted an even more accurate representation of that, you could do part B, which is saying repeat the points where x equals 3, which we already did, but the other point is going to be at x equals 3.001. And you can see that this here is a lot closer to 3 than this one here. Okay, it's barely moved away at all from 3, so it's going to create a much shorter secant, which will give us a more accurate instantaneous rate of change. So, doing the same process again, we're finding out the y equivalent when we substitute in 3.001. Here we get this value of y. And we're going to again find out the gradient between the 2 points. This value, take away this value, divided by this value, take away this value, and we get 5.547. Cool. You see it's even more accurate than that one there. So it says that, and if you wanted to really know, the true instantaneous rate of change is actually at x equals 3 is 5.5452. So you can see this is a lot more accurate than this one here to what it is. If you made this number even smaller, 3.000001, you would get even closer to that there. Perfect. Alrighty, I hope that you have fun looking at this particular exercise. Bye for now.